Hi, everybody. Welcome to this AI Horizons Wharton webinar. And it is a pleasure to be able to host this webinar on the impact of AI on abilities and skills. These webinars that we're running this fall are drawn from our inaugural conference on AI and the future of work that AI at Wharton organized and held on May 22 and 23rd at our campus here in Philadelphia. The conference was an exceptional event where we saw hundreds of participants from academia and industry gather together to listen to the latest insights and cutting-edge work on the impact of AI in the workplace. And what we decided to do is to invite some of the presenters at that conference to join us for a number of webinars where we are giving them a chance to tell about their work to a broader audience online. So it's a pleasure here today to be able to host three very interesting presentations on the way that AI is impacting human skills and human abilities, and also the abilities of the AI systems themselves. And so I think it's a very interesting, important topic. I know many organizations and the social sciences are worrying about this and wondering what the impact might be. And so we have three wonderful speakers today to help us learn about this topic. And the first one is going to be Seung-Woo Cho, who is an assistant professor of economics at the U.S. Military Academy at West Point. And he will be presenting a paper on the effect of robot assistance on skills, and we'll be learning about the impact of AI in sports. The second presenter is going to be Antonis Stamatogiannakis, who is an assistant professor of marketing at IE Business School, Instituto de Empresa Business School in Madrid in Spain. He's going to be talking about the debunking of assumptions about AI behavior. So in this case, we'll see a very interesting audit of AI systems and what they actually do. And the third presentation is going to be Shi Kang, who is an assistant professor of strategy and economics at Vanderbilt University. And she will be presenting a very interesting field experiment on machine predictions and causal explanations. Okay, I'm going to leave it now to the speakers. We'll have three presentations, fairly brief, just a summary of the work. And then after that, we'll have a conversation about the research and the bigger picture. Okay, with that, I'm going to leave the floor to Seung-Woo Cho to tell you about the effect of robot assistance on skills.
Okay, thank you. So let me share my screen and get started. Okay, so hi everyone, I'm Seung-Woo Cho, and I'm an assistant professor at West Point, and I'm very excited to talk about my paper, The Effect of Robot Assistance on Skills. Thank you for inviting me to this webinar. So in this paper, I ask a very broad question of how does working with robots change human capital? So in particular, first, what are the gains from adopting robot assistance on the assisted workers? And second, I ask what happens to the workers when the robot is removed and when the workers lose access to this technology. In particular, do they lose skills? So I study the implementation of the automated ball strike system in professional baseball leagues. Here, the robot or AI system is utilizing the sophisticated hardware and software algorithms to tracking pitches and assisting umpires making a ball strike decisions. But examining the impact of technology assistance on human capital is empirically challenging. But professional baseball leagues provide several advantages answering these questions. First, I have a new granular data set. In particular, I observed the worker-specific usage of technology, so I know exactly which umpires were assisted by a robot and those umpires who weren't. Also here, I have unique and precise measures of individual level of productivity, so I observed the decisions solely made by the umpire, and as well as whether the decisions were correct or not. Second, there is a substantial variation in the implementation of robots, providing different multiple natural experiments. There are 11 different leagues in the minor league system, of which only some implemented the robots. And with umpires potentially moving across leagues, I observed their behaviors and their performance before, with robots, and after the robot adoption, but without robots. So I employ a difference in differences design, exploiting the staggered adoption of robots across leagues, and also the umpires moving across leagues. This approach, in words, compares the change in the performance of umpires before and after using robots to the change in the performance of umpires that have never used the robots. Now, let me introduce the setting and the data briefly. So home plate umpires are tasked with determining whether thrown pitches are balls or strikes. The umpire must solely determine whether a pitch crosses the strike zone or not, which is the decision guideline used by the umpire. The strike zone is defined as an imaginary rectangular region over the home plate that extends roughly between the batter's shoulders and kneecap and has a dimension of about 20 by 25 inches. These split-second decisions are subject to human error and subjective judgment, potentially undermining accuracy, fairness, and consistency in determining the outcome of each pitch. So despite their efforts, the umpire's efforts to strive for consistency and high accuracy, umpires sometimes make mistakes and controversial calls. And because umpires' decisions are subject to human error and judgment, the Major League Baseball decided to experiment with the automated ball strike system, which can provide reliable assistance, ensuring accuracy and consistency across games and also within games. So how does this system actually work? After a pitch is thrown in a game, multiple cameras placed around the stadium captures the ball's flight path from different angles. Then the system identifies the exact pitch location and uses a calibrated strike zone personalized for each batter to make a ball strike decision. The call is then finally communicated through an earpiece to a home plate umpire standing physically behind the plate, who physically makes the decision. So starting in 2021, the Major League began experimenting with robot assistants, and positive results in consistency and reliability led to an expansion of the system throughout the minor leagues. So I used the universe of the Major League and minor league pitch level data from 2017 to 2023 seasons, and I gathered data for over 22 million pitches that include detailed pitch characteristics. Specifically, I have the information on X and Y pitch coordinates of every pitch as it crosses the strike zone, and I have the dimension of the strike zone for each batter. So I collect data from about 62,000 games that include the various game characteristics and, importantly, the umpire overseeing the game. So the final data set here has over 8.8 million called pitches with about 700 unique umpires. So let me briefly introduce the empirical strategy and show the results. So there are 11 different leagues in the minor league system, with each league providing a stage for experimental rule changes, and the umpires can move across leagues. So let me take an umpire that worked in AAA Pacific League in 2022, where the robot was implemented as an example. I can observe where these umpires worked without robot in 2021, which is the pre-period. And in 2022, they were assisted by robot, and I observed them in the following year in 2023. If the umpires moved to Major League, they worked without robot when they moved. So I exploit the staggered adoption of robot assistance over time and the umpires moving across leagues in a difference in differences framework. So I compared the performance of umpires who use the robots to those umpires who are never assisted at the times before, while using the robots, after, but without robots. So first, I ask, how do umpires change with robot assistance? So robot assistance works remarkably well. In month, when a robot helps calling the game, pitches are on average 6.4% more likely to be correctly called. So this finding confirms our general belief that robots help humans to perform higher quality work. But following robot implementation, umpires can move to another league where they are asked to perform the task of calling pitches again without assistance. In this month, post-robot, but now having lost access to robots, the umpires are 2.0 percentage points less accurate relative to the pre-assistance period, suffering a huge, significant skill decline. A 2% decline here is roughly equal to taking a median umpire down to the bottom 5th percentile. Now, is this skill depreciation a result of time away from the task? To examine whether robot assistance has a distinct impact from time of work, I examined a different treatment when some umpires abruptly experienced a year-long interruption in their careers due to the COVID-19 pandemic. In 2020, the COVID-19 pandemic canceled the entire minor league baseball season, but not the major league season. Therefore, the minor league umpires experienced a season-long unemployment in which they did not engage in the task, whereas the major league umpires did. So I compared the minor league umpires and the major league umpires in a difference in differences framework and find that the minor league umpires did marginally lose skills following the pause. So in the first month since the leagues restarted, the umpires faced a skill decline of 0.8 percentage points, statistically significant at the 10% level in the blue here. They quickly bounced back, however, starting from the second month of return. Collectively, these results suggest and imply that the skill depreciation stemming from robot implementation is larger than the time away effects from work. And these findings raise another important question of whether introduction of robot assistance impacts other skills as well. Here, I compare the outcomes of umpires who are assisted by the robots in 2022 to those who are not in the following year when working as the first base umpire, whose most crucial task is to make decisions on whether a base runner is safe or not. Here, the umpires who were previously assisted by robots face about 0.1 more challenges or replay review requests per game. And also the number of challenges being overturned has also increased by 0.09 per game. Collectively, these findings imply that the skill depreciation extends beyond the robot assist test because the first base umpires are not assisted by the technology here. So to conclude, in this project, I examined how does work with robots change human capital by studying umpires' decision accuracy in professional baseball settings. I first found that the umpires perform better with robot assistance, consistent with robots increasing efficiency and productivity in many settings. However, umpires suffer a significant skill decline below the pre-assistance period when they are required to take the task again. Finally, I find that the umpires suffer a decline in performance for other tasks as well. These findings, I think, raise important questions for future research and have large policy implications. And studying the impact of automation on human workers' skills will be essential for proactively addressing the challenges, but also the opportunities brought by the technological advancements like AI. The decline in performance for related tasks here that I find here suggests relevance and transferability to a wide range of other occupational settings that might require similar skill sets. Thank you.
Thank you, Sungwoo. Very interesting, excellent presentation. And now on to the next presenter. Antonis, want to share your screen?
Yes. So thanks for the opportunity to be here and to present this research that I've done together with my brilliant co-authors, Arsham and Seper, who are two PhD students at IE and at Erasmus University, and my colleagues at IE, Dilne and David. And in this research, we're basically studying and we're exploring some assumptions that underlie AI behavior. So some introduction. So AI right now is everywhere. There are hundreds of millions of users every week. And artificial intelligence is involved in basically every human activity, medicine, law, education, and so on. In business and organizations, there are two expectations that AI might replace humans and, alternatively, although not excluding each other, it might be used to aid humans. Now, both of these expectations rest on the assumption that AI and humans share some type of understanding. So they think the same, or AI behaves similarly like humans. And of course, there is evidence in favor of that. So there's evidence that AI emulates human behavior, and there's other research that shows that not only it emulates human behavior, but in some cases, it even performs better than humans. At the same time, however, there are some questions. So first of all, there's evidence from narrow AI, and specifically, for instance, from AI self-driving, which obviously alleviates some problems that human driving has, but also brings some new problems that are unique to it. And most importantly, our research team basically has observed that there's a lack of fair tests when we compare AI and human behavior. So a fair test we define as one that would not only test if AI does better or worse than humans, but whether it can make mistakes that are different than the mistakes that humans usually make. This is our first research question, is whether AI, basically LLMs, make mistakes, and whether these mistakes are the same or different than the mistakes that humans make. There are two more assumptions we want to study, and I'm going to use this slide here to explain them. So the first of all is that, of course, the expectation is that as time goes by, the AI models become more and more powerful. And that's clearly, natural. There are more investments, better training, and so on. However, what we question is that the assumption that the more powerful models will necessarily be better. So Sam Altman here said that GPT-4 is the dumbest model that any of you will ever have to use again by a lot. So our question, which ties up to the first one, is that even if AI makes mistakes, then maybe future models will just correct it. But this rests on the assumption that the newer, smarter versions of the LLMs are going to be better than the predecessors. And the last assumption is what we call the unidimensionality. So usually AI is measured in a single dimension. And in this graph, it is the computation, it is the mathematical calculations based on which it was trained, or it can be the parameter that it uses. And usually the assumption is that the more specifications, the better the performance. So our question is there anything more than that? So similar to how people are not just more smart and less smart one from the other, are there differences between models that cannot be captured by their mere intelligence? So these are the three questions we're having. We studied those in the domains of heuristics and biases, 6 domains: transaction utility, anchoring and adjustment, endowment effect, the representativeness heuristic, the availability heuristic, and the framing. All of those are kind of the most important human bias and heuristics, and we have 9 studies in those. Our methodology is basically very simple. So we take the original experiment and we run it 4 times. Or we run it with GPT 3.5 and with GPT 4. In some cases, we ask the LLM to try to be objective and unbiased. In other cases, we don't ask it that question. And in some cases, we ask it to assume a role. And in other questions, in other cases, we don't ask it to assume that role. And we are trying to see what is going to happen. So this is the summary of our results. There's a lot of empirical data, so I'll try to summarize it over here. The first thing to note is that across the board, LLMs seem to be unbiased in some cases, so improving human performance, but most of the times they're biased like humans. So this is the red, this is the yellow cells that you can see. In our opinion, the most interesting thing is that sometimes they're biased uniquely. So they show a bias that is the reverse of what humans show. So for example, in the bias that humans have been shown to overpay, LLM in some cases underpays. So we don't know why this happens. In terms of monotonic improvement, we found in 2 heuristics, the representativeness and the availability, that GPT 3.5 basically lifted the human bias, but GPT 4 replicated the human bias. So the less advanced model did worse than the more advanced ones. And then about the unidimensionality, across studies, we find evidence that the differences that cannot be easily captured by how smart the model is. So the 2 models show differences in handling of risk, in a response variance, and in prompt handling. So overall, we found that LLMs partially emulate human behavior. However, in some cases, they show reverse biases than those humans do. We find that sometimes the less advanced models perform better than the more advanced ones. And also we find differences that are just not easy to explain with the current state of knowledge, for example, risk preferences. In terms of theory, very simply, we say that we cannot just use human theories for AI, and we need to understand when AI converges or diverges from human behavior. In terms of practice, about external validity, all our studies were done with the API that all the big corporations use. So this is what companies use. So all our results would be obtained even in a practitioner setting. For organizations, we suggest that replacing and aiding humans with vanilla models is not recommendable, because sometimes these models may just operate in the way opposite to humans. For the users, we raise caution, because when you use AI for recommendations, the AI might have some traits that are hidden and that might be against someone's preferences. And about developers, we basically ask whether it is so straightforward to discontinue an older model, given that in some dimensions it might overperform, it might do better than the more advanced models. In terms of policy, we just call for some transparency, so to know what each model is good at, so that users, corporations, or consumers can use what is right for their needs. And that's it. If there are any questions, we will take them later at the discussion. So thanks a lot.
Thank you very much, Anthony. It's very cool study. And then now, the last but not least presentation, we have Shi. Please, can you share your slides?
Well, thank you so much for the opportunity to share my work. My name is Shi Khan. I'm an assistant professor of strategy at Vanderbilt University. Today, I'm going to share my work that is joint work with Hunjin Kim from INSEAD. This paper is about machine predictions and causal explanations, and we gathered empirical evidence from a field experiment. So there's been so much hype and so much interest among the firms to adopt predictive algorithm powered by AI to support decision makings. We've seen research that analyze how algorithms are impacting decisions in the context of human resource practice, in managing manufacturing plans, and in innovations such as drug development. And because of the algorithm would leverage large data and computing powers, it often translates to better predictions. But sometimes we see that the better predictions not necessarily contribute to an improved decision, partly because of this notion of algorithm aversion. So despite all this interest centered around decision per se, we said that there is limited insight on another important aspect of human-assisted decision, human decision-making assisted by AI, and that is how algorithms might impact not just the decision themselves, but how decision makers can develop and explain their decisions. So why do we think offering causal explanations are important, especially in a managerial context? And that's because managers not only need to make good decisions, but they also need to offer sound causal explanations around it. For example, you can't just announce a merger acquisition deal without explaining to all the stakeholders why you're pursuing this, what are the underlying mental model, causal models around it. And offering good causal explanations is going to help managers mobilize resources and align interests among employees, other shareholders, investors. And one of the most important tasks of management is to provide causal explanations, to offer rationalizations and legitimization for activities that they undertake in an organization. So that leads us to the research question. How do machine predictions impact decision makers' causal explanations? There has been substantial theoretical ambiguity around this. On the one hand, machine predictions can complement the development of causal explanations because now it reduces the uncertainty of prediction, and that might improve judgment of the decision maker. In addition, by delegating some of the prediction task to the algorithm, you can free up managers' limited cognitive capacity such that they can free up the capacity to focus on more mentally demanding tasks. On the other hand, relying on machine predictions can worsen the causal explanations. First of all, it might affect the incentive of decision makers to exert effort in complex ways. In addition to that, delegating the prediction task to the algorithm might create excessive modularization, and that will make it more challenging for the decision makers to understand the system's complexity, the interconnection between all of the factors. There has been limited empirical evidence, partly because it's really challenging to observe and measure causal explanations in real business contexts. So our paper hoped to contribute to this discussion and fill in the gap by collaborating with one of the leading investments research company in the world and run a field experiment across mutual fund analysts by focusing on the analyst's decision and their causal explanations. So these analysts are tasked to assign forward-looking ratings of mutual funds in comparison to their peer competitors. In addition to this decision about rating, they will also write analyst report that provide coherent causal explanations and offer any additional supporting evidence. In this context, there is substantial heterogeneity across the type of decision. Some of it might be on the simpler side with fewer causal drivers to consider. Some of them would be really complex. And we also observe heterogeneity along analyst experience. Right? So in terms of the experiment design, we run this experiment across all of the 97 mutual fund analysts across the globe in a firm for 9 months. The first 3 months being a baseline data collection period, and the next 6 months were when we actually run experiment. The company had internally developed a proprietary machine learning algorithm that provide predictions on mutual fund ratings and has been back tested since 2015. The analysts are aware of the existence of this machine learning algorithm, but they previously don't have access to the machine predictions. Now, we randomly assigned analysts to the control group or the treatment group, where people in the control group will continue to do business as usual, and the people in treatment group will additionally receive a machine predictions as the decision-making aid. And we further randomize within the treatment group such that the treatment people who got treatment 1 will receive machine predictions alone, and people who receive the second version of the treatment would additionally get some explainability offered by Shapley values. So in terms of the outcome variables that we care both about the decision quality per se and the causal explanation being offered. So in order to operationalize the measurement of decision quality, we follow the finance and accounting literature to construct this risk-adjusted return of analysts' recommended funds. So in essence, this is evaluating whether the recommended fund would perform better, would generate excessive return after controlling for the risk it is undertaking. And when it comes to the most important outcome variable, which is the explanation quality, we first start by asking an internal expert committee within the firm to evaluate every single analyst's causal reasoning and assign a reasoning score on a scale of 1 to 10. And then we further support that analysis by keeping track of the number of causal drivers identified and reported in those causal explanations. And we further conduct text analysis using natural language processing tools and large language models to evaluate the analyst report's text. And leveraging this baseline data that we collected, we run a difference in differences model to study how does providing machine predictions affects people's decision quality and their reasoning and their causal explanations. All right, so here's the result in a nutshell. We found that on average, there isn't a significant impact of machine predictions on a decision or reasoning, but this noisy average effect actually masks important heterogeneity effects. We find that when we break down by the type of decisions and the type of analyst, we found that machine predictions actually improve simpler decisions, but worsen complex ones, especially for new analysts. And we identify a trade-off between better decisions and better causal explanations. Even when a new analyst, for example, got supported and made better predictions in terms of their decision quality, they actually suffer from worse causal explanations. So why are we seeing these effects? One of the possible mechanisms is that relying on machine predictions can actually lead analysts to have difficulty integrating machine predictions with their own causal models. And we observed some suggestive evidence that consistent with this. So the treated analysts who work with simpler decisions, and these people would suffer from a worse causal reasoning score as evaluated by the committee, self-report to rely more on the algorithms. As you can see here, these people who self-report that algorithms contribute more to their decision-making suffer from a worse causal explanations. We also see that these people would write shorter, less technical, and less coherent justifications in their analyst report. In addition to that, these are also the people who have a hard time narrowing down and identify a set of key causal drivers, all supporting to the sense that they seem to have a hard time reconciling and integrating to generate a good causal model. So what's the conclusion? We find that even when algorithms improve decisions, they may worsen causal explanations. It seems like machine prediction as a decision-making aid can be a double-edged sword. Despite the promise of free up cognitive capacity, algorithm may introduce complex effect on decision makers. And as we further think about how to integrate human and AI in one decision-making loop, we really need to do more experiment in order to understand not just how algorithms affect decisions themselves, but also how it affects other factors. So, thank you very much.
Thank you, Chi. And now we are coming to the discussion part of this session. And I'd like to kick it off with a general question. I'd like to invite all the three of you to share your thoughts on this general question. Then we'll see how we go from there. I have a curiosity, a question I would like to ask each of you. But I think if you take a step back and look at these three presentations, I think a very interesting picture emerges where we see that to some extent you could argue that with AI deployment, people sort of stop thinking to some extent. This is a bit maybe what you can take out of Sungwo's and Xi's presentation. And even if the decisions might be improved with the deployment of AI, that is actually a concern, either because at some point human experts will have to make a judgment without the AI, and then that deterioration of lack of practice and the deterioration of skills that Sungwo showed is then a problem, or because even if the decision is better, the lack of underlying causal inference and actually hard thinking about the problem might undermine other things that are important beyond the ultimate political decision, like she showed us. And adding to that, Antonio's research shows that basically AI has biases like our biases, and that these biases may actually sometimes even be different or vary over time in ways that we do not expect, and therefore you cannot easily make assumptions about what AI systems will be doing. So there is this additional compounding of a degree of unpredictability, especially in the context of generative AI tools. Okay, so with that kind of like a broad picture in mind, I find this like a tremendous set of papers. And I would like to ask each of you to just share some thoughts about your impression based on the findings in your own work, and maybe also on the findings of related work in your area. What do you think that right now one might be able to tentatively conclude about the general impact of AI on skills? And I'm speaking to academics. I know that you're always very reluctant to generalize far from the context of your studies, but I'd like you to take a little bit of a punt there and say, given the state of the literature, and obviously this literature is evolving very fast, and we're learning a lot more as time goes on, but right now, at this point in time, what do you think that are the broad strokes conclusions that one can draw? So, well, I'd like to start.
Yes, so it's really hard to generalize our findings, or my findings especially, because it's a very unique setting in baseball. But I think we all have some anecdotal evidences of AI or some sort of technology deteriorating our skill. If you are to drive a car, for example, now without a GPS system or navigation system, or like parking assistant, it might be very hard to park or navigate around the cities of something like Philadelphia, right? So I think the discussion will, in the future, center around what kind of skills are we trying to preserve. So some jobs like judges or doctors or like those have like high importance might require human oversight, even if the job itself or task itself is robot assisted. And also, like she's finding, we have some sort of trade-off between efficiency in making decisions, but also some loss in skills in making some reasonings or causal explanations. So I think there's going to be a shift in skill spectrum in the future where we are going to have some loss in skills in certain area, but that might be displaced to some other areas. So in my findings, I have the umpires losing skills in making ball strike decisions, and that was transferred into other non-robot assisted tasks. But given the limited setting where umpires are making limited sets of decisions, there could be an improvement in some other areas where umpires are now better allocate their mental resources on doing some other things, right? So I think there's going to be a skill shift within the spectrum in the future. And I think the discussion should center around what kind of skills we preserve in the future.
Thank you. I like that angle. I was pointing out, I was claiming that basically the research suggests that people stop thinking or that they think less deeply, and you have a more hopeful view and say, well, hopefully they're thinking about something else. Maybe that is useful too. And so the question will be, what kind of skills people are losing, what kind of skills people are gaining, and are we okay with that trade-off? Thank you. Antonis, what about from your perspective of running this extensive AI audits? What do you want to say about that?
Yeah, so the way I see it, it's kind of just like academics, in practice, people are still experimenting, how they can do and what they can do and how this AI revolution can be useful to them. And then in this kind of experimentation, I think there are probably different types of groups. So there are people who just don't try, and because of age barriers and technology barriers, it's likely that those people are at the top of many companies where there's a correlation between senior management and age. So those people might just not play with AI enough, and that might kind of inhibit its advancement. And then from the people who actually try, there are people who just don't see any value in it. And then for that, I think that both she's paper and my paper speak to that if I use it and I don't understand exactly what it's doing, if I use it and I see that the previous model gave me some results and the new one gives me something new, or that I ask it 10 times and it gives me different answers, that's kind of, all these behaviors by AI, they might be strange to people and say, okay, this is not ripe yet for utilization, so they might just skip it. Then you have the other set of people who are going to be the most persistent ones and who are going to reap the benefits. And then the big question is, are the benefits going to be for themselves, or can the benefits be diffused within organizations and within the society? And that's a different question, I guess. But I think that this is also a significant barrier, not only for AI, but with technology in general. The pioneers of technology, sometimes they have a difficult time to illustrate why this is so great.
Yeah, and I think it is, you're completely correct that I think for organizations, it is worth really thinking hard about how do we ensure that the learnings accumulated by people who are the ones who are tinkering, are trying, that are excited, percolate and disseminate across organizations so that everybody can benefit from those learnings. And in our own data, running a service of US executives, we do see that AI adoption, the intensive adoption, decreases with an increase in age. And you're right to point out that the more senior people therefore tend to be those with least experience in the system, so which might be in itself problematic. Thank you, Antonis. So now on to Chi. What would you like to add to that conversation?
Yeah, so I definitely second the idea that it depends on the people, it depends on your tenure. And I think what tenure is pointed to is possibly domain expertise. And that is critical when it comes to combining AI suggestions with human insights. So like senior people who tend to have a lot of domain expertise are more susceptible, that they exhibit more algorithmic aversion. They're more reluctant to incorporate AI into their framework. On the other hand, junior people tend to are more open-minded and tend to embrace the new technology a little bit more. But then the concern is that many of them lack the domain expertise. And as my research suggests, the newer analysts might have a difficulty incorporating the machine predictions with their own mental model because they lack domain expertise. They have a hard time evaluating what the algorithm is essentially suggesting, what factors is valuable, and you should add that to integrate that into your mental model. And because they haven't had enough experience and time to build a solid thinking framework around their expertise yet, it is even harder for them to just take a piece and then add that to their structure, their structure they're building without it falling apart. So that is the thing that I wanted to highlight, is to consider domain expertise as the building block of human AI collaboration, and how we might want to design a different workflow and structure depending on people's expertise.
Yeah, Yeah, very, very good point, I think. And what I really liked about your paper is the emphasis on causal inference and causal reasoning, because if you think about trying to, a situation where AI is being deployed across organizations, and we're trying to find a role for human and artificial intelligence in this new brave world, then there is a question of saying what kind of complementarities or distinct abilities can we identify in one or the other. And I think one of the obvious cases in which human intelligence still at this point has a massive advantage over machines is causal inference, because obviously those machine learning models are prediction machines, and therefore they're not designed, they're not architected to think in terms of causal models and mental models. So in that sense, I think, for all the improvements that we've seen in recent years, I think that is going to be, moving forward, a crucial element of, the way that human expertise is going to pay dividends in organization is going to be through causal inference. So I found that really interesting finding. I actually have one maybe question for each of you, just to go into a little bit more detail of a couple of elements of your work, and then we'll wrap up after that. And I'll like to start with the Sungo. And I was thinking about your finding that the deterioration of skill appears to generalize beyond the task being automated. Very fascinating finding, and obviously, this has to be extended and validated in other contexts. But I think it's a quite important finding. But the question for me would be, what do you think is going on? What might be the reason why there would be that spillover effect? Because you don't expect that to be necessarily there, wouldn't you? Did you expect to find it?
All right, so I think you are referring to the finding that the umpires who were assisted by a robot, if they work as a first base umpire, they lose skills in that task. So the one reason that might be happening here is that umpires might be fearing about their job in overall, so they lack focus and practice. So I also have a finding where umpires, if they were assisted by a robot for longer duration, they suffer worse than larger depreciation. So it could be that umpires might be just staying away from the game for very long, and they are just losing overall focus and skill in all the related areas. And also, it's the first base umpire's task is very similar to the home plate umpire's task. So they require visual sharpness and mental effort. So it could be just umpires losing that area of skill overall. It's hard to evaluate what happens to the overall game, umpires' other task that's more unrelated to the task that home plate umpires were doing. It could be interesting to see if the umpires are actually better at managing the game overall, because they are now allocating their mental resources to some other area. But overall here, I think the task is very similar. So I think substitutability and complementarity of skills here could be the reason why I see a decline in that area as well.
Yeah. I like, so you say that two possible explanations. One is a overlapping skill. So you develop this skill on one, you automatically also be skilling in the other. But the one could be a general disengagement from the game, that you are basically a bit less focused, and so forth. That will be interesting future research to try to piece apart. Moving to Antonis, what do you think is the role of prompt engineering and prompting? Are you hopeful about the way of avoiding some of these biases or controlling some of this unexpected variance through prompt engineering? Did you try to see whether some of these biases are robust to the way that you ask a question, or there is a way to somehow correct?
Yes, so let me, if you don't mind, let me go back a little bit here to the relevant slide. So we did try variations of prompt engineering, and we basically found a very messy picture. So in this table, the debiased role, so the second and the fourth column refer to variations in prompting. So you see that most of the time you have consistent results, and sometimes you have the prompt doing better, sometimes you have the prompt doing worse. And most importantly, something that I didn't have time to cover is that we have differences for prompt handling. So how the two models respond to the same prompt, and the prompt can be very, very simple, like, please try to be as objective and unbiased as possible, because it's a question that answers are frequently erroneous, something like that. The two models just give different answers to this very simple thing. So they handle prompts differently. So I also think that prompt engineering can help in alleviate many of those biases. But right now, I see, and based on our findings, that this can only be done at a very local level. So you should take the LLM and you should prompt it, and you should try to find the prompts that work well for your problem. And those prompts are not going to be generalizable next month or to a similar problem a colleague faces, and so on. So we didn't find evidence that, if you use the prompt, it's going to solve some problems consistently with all the prompts we tried. But of course, prompt engineering, is a universe. So, there might be something that we didn't check.
Yeah, so I like your answer saying maybe very task-specific prompt would be able to help the network calibrate some of its judgments. I think that's something will be interesting to test in future research. Thank you. Now, if I can move on to the last question would be about the deployment of AI in organizations. And you had the luck to be able to, or the brilliance of being able to run a field experiment with sophisticated knowledge workers. And so a question for you will be based on that experience. Do you have any suggestions of about how AI might be deployed in a way that minimizes the risk of AI deployment, basically creating a negative effect on human experts' causal inference processes? What do you think an organization can do if they still want to benefit from the AI in terms of better decisions?
Yeah, I think try and error is definitely the way to go. And running causal, like field experiment, randomized trial, controlled trials, even without the help of scientists, social scientists, should be considered an important practice even within organizations. So the typical way of implementing any new policy, new tools that I've observed among a company is that, okay, they come up with this new tool and decided this is a good idea and just like implement it across the company, and then wait for a result. So then the best inference you can get is the pre-post comparison. And there's so many confounding factors. You missed out on the opportunity to learn from that experience. So, and firms now understand importance of doing A/B testing in a lot of the settings. And I think that practice can also be adopted when it comes to technology adoption, when it comes to providing AI suggestion assistance to their employees. So I think rolling out on a smaller scales, test out all of the complementary resources, different configurations of workflow, adjustment, training, incentive structure is going to allow the firm itself to learn so much about the context-specific configurations. And yeah, so we can only generalize so much insights. And when it comes to a firm-specific question structure, it really comes down to how well you can experiment and learn from that experiment.
Thank you. Yeah, test and learn. And I think the value of investing in learning, and for example, keep a control condition to make sure that you have a randomized baseline to check the effect of any policy. I think that's a very good learning, which as a behavioral scientist, I very much endorse. Okay, thank you all. I think this was excellent. I think you did a wonderful job. Congratulations for really interesting work, and I wish you all the best in getting it published.